I'm Krishnamurthy, Faculty of Mathematics of VK Center for Education. I'm going to discuss on the Introduction to Matrices of Chapter 3rd in Class 12 CBSE. We'll throw some light on this topic today, where initial understanding on matrices could become clearer to all. Matrix itself, it gives a meaning, the arrangement of completely collected some collection of entries, collection of items, some data. So what's a matrix? It speaks about any set of collections of some grouped items. When we arrange it in a sequential order, we call this mainly as rows and columns. Say A11, A12, A21, A22. This way arranged pattern is known as a matrix. We start calling A11 and A12 as the first row entries, A21 and A22 as the second row entries. Or we can say A11 and A21 as column 1 entries, A12 and A22 as column 2 entries. By the way, the entries of a collection of items put together, written within the square bracket, is called a matrix, and whose order will be mentioned in the form of number of rows and number of columns. When we generalize it, A11, A12 and so on up to A1n, A21, A22 and so on up to A2n, and when we further proceeded, AM1, AM2 up to AMN, this pertains to a matrix of size m into n. There are mn elements where n rows of entries are involved and n columns of entries are involved. Representation of the order of the matrix, this way we are explaining. How do we represent a matrix? When we have sometimes some set of entries, set of matrices followed, in plural form we call it as matrices, and all of them can be applied with algebra of matrices called, we can add them, we can subtract them, we can even multiply over them, and all the operational features which we do in normal real numbers can be done on matrices also. So matrix follows all operational features also. So this deals with algebra of matrices. The compatibility rules speaks about how can we add the two matrices or more than two matrices or subtract them. And the last point will describe properties of addition of matrices or over scalar multiplication of a scalar with a matrix chosen. It's an introduction, or we can call it as an objective. In this frame we are explaining very clearly it is an arrangement of all entries in rows and columns. Its order will be normally denoted by number of rows and number of columns displayed in the chosen matrix. In general we write in the form A11. The suffix explains the first row, first column entry. The second entry A12 explains first row, second column position entries. The positional entries with which the representation is given. Actually, A12 may be any data, so it may be a number 7. It may be a name call. It could be anything. It may be any real number, even some big Latin word, anything that we can use. But see, these representations indicate only the positional aspect, and these are called subscripted variables. If I talk about A21, it's in the second row, first column position entry. By the way, we say n rows and n columns are involved, and there are mn elements. Maybe we are writing a model, a 3x3 matrix, where 9 entries are mentioned, where this represents positional features are kept, and thereby we say it is a 3x3 matrix. And when the number of rows and number of columns are being equal, we could call this as a square matrix. Further, we explain in the matrix A, there are m rows involved and there are n columns involved. In matrix B, there are 3 rows, 1, 2, 3 in the first row, 4, 5, 6 in the second row, and 7, 8, 9 in the third row. And 3 columns, 1, 4, 7 is column 1, 2, 5, 8 is in the column 2, and 3, 6, 9 are in the column 3. There are totally 9 elements. In plural form, if we take 3 different matrices, it could be of order 2 by 3, 3 by 4, or 2 by 2. So it explains clearly the order of the matrices could be any one. By the way, number of elements we have considered, it speaks about it, or it depends on that. Totally there are m into n elements in a matrix where m and n are natural numbers. Let us take a specific question. How many matrices of different order could be formed from 12 entries? There are 12 entries we have considered. The possible order of matrices from 12 given entries using all the entries taken at a time could be, see, it's from the way we can define the factors of the number chosen. 12 being the number chosen, 1 12 is 12, 2 6 are 12, 3 4s are 12, 4 3s are 12, 6 2s are 12, and 12 1 is 12. So in all possibilities we have planned it. The question was to identify, or it is aimed at eliciting from the children that how many possible ways of arrangements the same set of 12 entries may be given. So 1 by 12, it would represent only one row being involved. We can call it as a row matrix. 2 by 6 is known as a rectangular matrix. There are only 2 rows but 6 columns are there. This is also rectangular, 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 and this could be called. There are 12 rows but only 1 column. Then it's called a column matrix. Even a finite number of elements can be expressed in the way of different orders. So this is what the first bulletin point explains. If the number of elements chosen is a prime number, then the number of possible orders are normally 2 itself. If the number of elements chosen being a prime number, we can say there are p elements involved in the matrix. It could be written in the form either 1 by p or p by 1 only, by p being a prime number chosen. Similar way, when we have chosen a composite number as a number of elements to represent the matrix, if the number of elements chosen is a composite number, the number of possible orders will be equal to number of its factors. Like now we have seen there are 12 letters. Being a composite number, it gives us 6 possible ways of defining them. Let's speak about the types of matrices. What are the different types of matrices we can consider? We were slightly before speaking about the row matrix. Row matrix, the very name itself explains to you, there is only one row involved. A matrix which has only one row of entries of order 1 by n. But the second notation indicates there could be any number of columns where the number of rows is only 1. We can call this as a row matrix. Similarly, column matrix is a matrix where only one column is involved. We were writing in a form, or we are mentioning in the form m by 1. The reading pattern for the representation of any matrix is m by n. There are m rows involved, n columns involved. A matrix is said to be rectangular if the number of rows, say m, the number of columns, say n, are not equal. We may be considering a 2 by 3 matrix where number of rows being 2, number of columns being 3, we could call it as a rectangular matrix. Horizontal matrix speaks about this point which I was mentioning recently, a matrix of order m by n where n is less than n. 2 by 3 matrix which I spoke about now, where the number of rows are lesser than the number of columns, or the way the matrix defined itself is established, it's called a horizontal matrix. Vertical matrix is the opposite of the same which we have chosen recently, a matrix of order m by n where n is greater than n. Null matrix or void matrix and the zero matrix are all of useful in many of the applications directly as an identity. They contain only zeros in the position. A matrix is said to be null matrix if all its elements are zeros. Square matrix, a matrix whose number of rows and number of columns shall be equal. If there are equal number of rows and equal number of columns, we call that matrix as a square matrix. A matrix of order 2 by 2, a matrix of order 3 by 3. So these square matrices could be directly even mentioned as matrix of order 3 itself, instead of fully mentioning as 3 by 3. Further to the types of matrices we have, it's a different type rather than the previous one. Diagonal matrix is a square matrix, where its leading diagonal elements should be non-zero elements. It should be a square matrix where the leading diagonal elements should be non-zero elements, and other than them all should be zeros. So we are mentioning here Aij, A general entry of a matrix Aij is a positional value. If it is 0 itself, the value 0 itself for every I not equal to j. The actual diagonal positional entries are probably called A11, A12, A33 and so on up to ANN. So the indication is very clear here. The matrix A could be even rewritten in the form diag of A11, A12 up to ANN. The diagonal matrix could be written in this form. It's a notation where we have to remember this particular point only. Aij becomes 0 whenever I is not equal to j. Say A12, A13, A21, A32, all these are satisfying this condition. I is not equal to j. Those positional entries will be 0. So I can write in the way, say the diagonal entries are 2, 3, 5, the other entries are zeros. So we can call this as a diagonal matrix. We have square matrix in which every non-diagonal elements are zeros and all diagonal elements are equal. So we are defining further a subsidiary condition further to the diagonal matrix, say scalar matrix. Scalar matrix is going to be a matrix of the same type where all the leading diagonal entries should be the same element. All the leading diagonal elements should be the same. So here also we are mentioning the conditions clearly. Aij should be equal to 0 for I is not equal to j, and Aij should be the same non-zero constant any real number whenever I and j are equal. The last form of this type is identity matrix. It could be also called as unit matrix or identity matrix, where it should be a square matrix, or it may be even called directly as a scalar matrix, where the diagonal elements should be 1 itself. The diagonal elements should be 1 itself. 1, 0, 0, 0, 1, 0, 0, 0, 1. It's a matrix of order 3 by 3, matrix of order 3 by 3, and this also following the same paths. Further to the same, these all conditionally developed types of matrices would help us to consider the applications directly in the further application. When we go for the application problems, this would help us to quickly decide the results of some questions. Here we speak about upper triangular matrix where the entries below the diagonal are all zeros. Upper triangular matrix explains about it should be a square matrix A, and all the elements Aij should be equal to 0 whenever A is greater than j. The position of this is A21, 2 is greater than 1, A31, 3 is greater than 1, A32, 3 is greater than 2. So these positional entries are zeros. We can remember easily upper triangular where the lower part of the entries are zeros. Similar to the same, lower triangular matrix follow the similar norms, just the opposite inside. The way it is explained, a square matrix in which Aij should be equal to 0 whenever I is less than j. Whenever I is less than j, here the positional entry is A12, 1 is less than 2. The positional entry is A13, 1 is less than 3. And it is positional entry is A23, 2 is less than 3. So these conditions, as it satisfies and those entries are 0, we could call them as lower triangular matrix. Or maybe it is easy to remember the triangular region above the leading diagonal being 0. Above the leading diagonal being 0, it is mentioned as lower triangular. Submatrix is mostly helpful for our determinant purpose in the next chapter, where a matrix which could be further obtained by eliminating a row or column, a row and a column, or maybe some selected rows and columns. The obtained the new one would be called submatrix. From a 4 by 4 matrix, we have deleted the first column and first row. We will be getting now 3 by 3 matrix of order 3 itself. It will be of a square matrix once again. Equality of two matrices. Two matrices A and B are said to be equal if both have the same order. The condition number 1 is they are of the same order. The first matrix is 2 by 3. The second matrix is also 2 by 3. And when we are comparing the corresponding components, those positional entries shall be same, provided A has elements say 2x, 3y, and B has elements same A 3 and B 4. We can compare the corresponding entries and bring the answer. X position entry is 3, Y position entry is 4, and in place of A we have 2, and in place of B we have 3. The corresponding positional entries are compared. In the case of matrices, the equality matrices is to compare the positional entries, and they are all equal in its nature. The principal diagonal of a matrix. In a square matrix, the diagonal from the first element of the first row to the last element of the last row is called the principal diagonal. The other diagonal will be called the trailing diagonal, or it is also known to be the leading diagonal entries of the matrix. So when we generalize it, A11, A12, A13, A21, A22, A23, A31, A32 and A33. These entries are called leading diagonal entries, where I is equal to j. The other form is called the trailing diagonal entries. That is called the trailing diagonal. We shall enter into the operational processes of matrices, where algebra of matrices explains about two matrices can be added only when they have the same order. I have a matrix of order 3 by 4. I can add the 3 by 4 matrix where the first element of the first matrix can be added with the first element of the second matrix. The definition or the compatibility rule is those corresponding positional entries are added and the added matrix will be obtained. The sum matrix will be of the same order. The sum matrix will be of the same order. Here we have taken an example. It's a matrix of order 2 by 3. The other second matrix is also of the order 2 by 3. The sum is shown here, it is of order 2 by 3. The establishing point is two matrices can be added if they have the same order, and the adding rule is corresponding entries are added directly. So two or more matrices are considered. They all could be conformable for addition if they all have the same order. It's not that only two can be added, even 10 matrices can be added at a time, all having the same order. Another properties of addition. We have studied in real numbers the topic that two numbers can be added under what conditions. Here also, addition is defined in the previous frame, in the frame before. A plus B is defined, B plus A is also defined. By the way, here, the added result of the matrices A and B or of the matrices B and D would never differ. And that property is called a commutative law. Associativeness always speaks about three entries considered at a time. Where ABC are any three matrices and association being done in a different way. A and B are added first and then C is added later. B and C are added first and A is added later. By the way, it is not going to affect the result of the matrix, result of the addition of the matrices. This property is noted as associative property. These are the two things which are normally essential, and we used to give more importance to it. Existence of additive identity. We have seen in the very beginning frame that a matrix is said to be null matrix if all the entries are zeros. If all the entries are zeros. A zero matrix of order m by n is additive identity of all the time. For addition, A being any matrix of order, we can define null matrix of the same order. When added, we are going to get the same matrix as the result. So 0 is the unique element which is called the additive identity of the matrices of all addition processes concerned. Existence of additive inverse. The existence of additive inverse speaks about when I can get, if I added a matrix with answer 0. A being a chosen matrix with which I should add, my result would become 0. A being a chosen matrix with minus A, if I add always, I'm going to get the answer as 0. So for every matrix in such way, its opposite form, minus 1 of that gives us the additive inverse of the matrix. Cancellation law is directly explaining about the first matrix being same in both the cases. We especially mention it as left cancellation law. The right one being the same and the cancelled, it's called right cancellation law. In the last frame, where it speaks about A and B are two matrices of the same order, As the addition being defined, the subtraction is also defined. The corresponding entries are subtracted and the order of the difference matrix also will be of the same. We have already chosen a 3 by 2 matrix. I am subtracting the 3 by 2 matrix. The answer also will be a 3 by 2 matrix. When we multiply a matrix with k, it's a last stage, and under this particular type it's more important also. K being a non-zero real number, when we multiply a matrix with k, it gives a meaning. Say this D is the matrix we have already considered. I want to multiply with 3. It will give me the result 3 into 2, 3 into 0, 3 into 9, here 3 into 5, 15. So I am establishing a process where each entry should be added by, or sorry, multiplied by that particular non-zero constant. K into A plus B shows that A plus B added matrix is further multiplied by K, which will be always true with the condition that, or with the process proved that K and the KB added value. Okay, these points could explain clearly how these properties are true. We can even practice them properly at home, and in the next session, when the discussion session comes up, we can discuss on these things, and wherever the doubts arise, we'll be able to clear your doubts. All the best. Thank you and have a nice day.